Welcome back to the next section of Chapter 6. In this section, we're going to continue looking at statistics, but we're going to look at a very, very specific kind of statistics. We're going to look at specifically binomial distributions. I know in the last section, there was a lot of stuff, and a lot of it was review. There's a little bit of new stuff, but lots of little things. This one, it's really going to focus on one thing, but it is a little bit tricky. It has an equation that looks really kind of scary, but it's not as scary as it looks, and we'll see that in a few minutes when we get to it. This is the last official section of the chapter. We do have two more after this, however. So, let's look at our learning targets. First one, I can use the binomial theorem to expand a binomial raised to a power. Now, if that sounds familiar, it's because it is. We had this learning target way back in Chapter 6. It's something that we learned. Some people did it. Some people got around it by doing something much, much more difficult. And some people just didn't do it at all, and it hurt them in the long run. This is something that does not go away. Pre-calculus was doing it. In fact, pre-calculus was doing that just yesterday in a calculus chapter. So it keeps coming, and really, it's the easy way of doing stuff. The other ways are so much harder. So that's the first one. And then the second one is I can find binomial probabilities and test hypotheses. So, first let's look at binomial expansion. This is the thing that's review. If we remember, if we wanted to expand a plus b to the fourth, something plus something to a power, we can expand it out. There's a nice little pattern. In the beginning, we're going to have this, the a to the fourth, and then plus, we'll just go down a power. A to the third, plus a squared, plus a to the first, plus no a's. All right, we start out with this exponent, we go down a power. Then with this one, we're going to start out with the exponent, but on the other side. So we're going to have b to the fourth, and then b cubed, b squared, b, and then no b's. And after that, we just need to figure out the coefficients. And the coefficients came from Pascal's triangle. That triangle that's just kind of almost randomly created, but it has so many uses. We're going to find another one today. So if we remember Pascal's triangle, it starts out with a 1, and then 1, 1, and then every number is going to be the sum of the two above it. So 1 plus 1 is 2. 1 plus 2 is 3. 3 plus 3 is 6. 4 plus 6 is 10. 1 plus 4 is 5. And we can continue that as far down as we want. And so that's how it's created. We're going to look at the row. They all start out 1. We want that second number to be the same as their exponent. So we're going to look at the row that starts 1, 4. 6, 4, 1. And we're just going to put those numbers in front of our terms in order. So we'll have 1, 4, 6, 4, 1. And notice there's even the right number of terms for the right number of numbers. It's really quite magic. And so we get a to the fourth plus 4a cubed b plus 6a squared b squared plus ab cubed plus b to the fourth. And we did that, and I mean, there's a lot of explanation there, but I mean, just doing it, you just write it down. That was instead of going a plus b times a plus b times a plus b, and then times a plus b again. That gets really long and obnoxious. And so we might be thinking, why are we doing this again? This actually relates to binomial probability. The first piece is the numbers in Pascal's triangle actually relate. If we have Pascal's triangle, and we take our combinations. Remember back at the beginning of the chapter, we had combinations and permutations. Take combinations. They get us the numbers. 0 to 0 is 1. 1 choose 0 is 1. 1 choose 1 is 1. 2 choose 0 is 1. 2 choose 1 is 2. 2 choose 2 is 1. 3 choose 0 is 1. 3 choose 1 is 3. 3 choose 2 is 3. 3 choose 3 is 1. And this continues going down. For example, if we had 5 choose 3, we would go to the fifth row. Now this is tricky because it starts out with row 0. 1, 2, 3, 4, 5. And we'd go in 3 places. Again, it starts out 0, 1, 2, 3. So 5 choose 3 equals 10. And so we can use Pascal's triangle to help us with our combinations. We can use our combinations to figure out the line. If we had something to the 8th power, we used to have to write out Pascal's triangle all the way down to the 8th line. Now we could just do 8 choose 0, 8 choose 1, 8 choose 2, 8 choose 3, 8 choose 4, 8 choose 5, 8 choose 6, 8 choose 7, and then 8 choose 8. And we wouldn't have to create that triangle all the way down to that point. Will you have to go out that far? No, not particularly. But it's nice to know that you can. And so this, if we take this and we wanted to generalize it back to the binomial expansion using our coefficients, we get what's called the binomial theorem. And the binomial theorem says for any whole number n, if we have something plus something to the nth power, notice our x's, that first thing, n, n minus 1, n minus 2, yada, 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 to the 1, and then to the nothing. So we just keep going down by 1. The y's start out over here. N, n minus 1, blah, 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 1, and then nothing. And then the coefficients, n choose 0, n choose 1, n choose 2, n choose 3, n choose 4, n choose 5, all the way to n choose n. And we can expand anything that is something plus something to a power. Now remember, that includes something minus something to a power, because we just need to make that y value negative, plug it in, so it would be negative something in each of the places, and it works out perfectly fine. So let's try one of these. Now it's been a while, so let's try one. Let's expand y plus 2 to the 5th. All right, so Pascal's triangle is right up here, so you don't even need to find your combinations. See if you can follow the pattern. Expand y plus 2 to the 5th. Go ahead, pause, and come back in a minute when you're ready. Did you do it? Go back and actually do this. All right, did you do it that time? I hope so. That's how you get the benefit of this. So when we expand it, we're going to start out with y to the 5th, then y to the 4th, cubed, squared, 1y, and then there's no y's. 2 to the 5th, 4th, cubed, squared, 1, 2, no 2's. And then we can simplify. 5 times 2 is 10, 2 squared is 4, times 10 is 40, 2 cubed is 8, times 10 is 80, 2 to the 4th is 16, times 5 is 80, and 2 to the 5th is 32. And just write down, and there we go. We expand it. Expanding this, I would literally show these 2 steps. That's all that has to happen. If we were to multiply this out, we'd have y plus 2 times y plus 2, multiply those 2 out, then another y plus 2 times y plus 2, and then we'd have another y plus 2. I'd multiply the first 2 products together, and then I'd have to multiply the third one to it, and it gets ugly. It's 2 steps. It doesn't matter what the exponent is, you can do it in 2 steps. So that's binomial expansion. That was something that we've done. Now let's get to binomial distributions. Get to the probability. And we'll actually see where the binomial theorem comes in here. The first thing with binomial distributions is we need to look at the binomial setting. This book calls it a binomial experiment. But certain things have to happen for it to be considered binomial. And that's the binomial setting. The first thing, actually the first two things, the way I write it, I always combine it into one, which the only problem is I keep looking for the fourth thing, but I have it. We have a fixed number of independent trials, which we call n. We're going to do something n times. I say this is 2 because it has a fixed number of trials, and the second one is each trial is independent. Write it as 1. The second piece of the setting is that each trial has only 2 possible outcomes. It's either a success or it's a failure. You're flipping coins, you get ahead or you don't get ahead. You're taking a test, you pass or you fail. Now, success and failure is just you get what you want or you don't. If we're looking at, say, driving cars and we're looking at accidents, a probability of success might be the probability that you get into an accident. That is not generally what we consider a success in the real world, but as far as the probability is going on, it's success. Success does not mean a good thing. It means you got what you were looking for in the situation. So it's either success or failure. You can use this for things like dice. You either get a 1 or you don't get a 1. You get a 2 or 3 or you don't get a 2 or 3. So when if you're recording data, the only thing you can really write is yes or no. You either got what you were looking for or you didn't. You wouldn't write down what you actually rolled. It's yes or no. And then the probability of success for each trial is going to be the same, and we call that P. So we have a fixed number of trials, only 2 possible things, the success is always the same, and then we look for what's the probability of getting a certain number of successes in those fixed trials. But before we get there, so if the probability of success is P, that means the probability of failure is going to be 1 minus P, which we also call Q. I don't know exactly why we use Q, probably because of the proximity in the alphabet. But, so the probability of success is P, probability of failure is Q, and I say that because we're going to use it in the equation. And so what are some examples of some binomial settings? Let's say Abby is shooting free throws in the big game. What's the probability that she makes 8 of 9 shots? So, do we have a fixed number of trials? Yep, there's 9 shots. Are they all independent of each other? As far as we can tell, one shot shouldn't affect the other shot. I know there's probably some psychological deal going on, but yeah, they're independent. Each has 2 possible outcomes. Either she makes the basket or she doesn't make it. And then the probability of success on each trial is the same. She would have a consistent free throw percentage. And so this is, and we don't know the percentage right in this, but this would be an example of something where we could use binomial distributions with, and we will in a minute. Another example, Grant is rolling dice. What is the probability that 4 out of the 5 rolls will be 6s? So he's rolling 5 times. It's a fixed number. Rolling dice, so they're independent. 2 possible outcomes. It's either 6 or it's not a 6. And the probability of getting a 6 is going to be the same each time. So rolling dice, this is going to be a binomial problem. And then lastly, Shelby's tearing the bottom off of a piece of paper. What is the probability that it is perfectly on the line at least 4 out of 5 times? So we have a fixed number of trials, 5. Each time should be independent. 2 possible outcomes, either it's perfect or it's not. And the probability of success each time should be about the same. And so this would be binomial. So let's do one of these problems. Let's start out with, we're going to do all of these. But let's start out with the baskets. So Abby is shooting free throws. What is the probability that she makes 8 of 9 shots? So we do need another piece of information. we need to know what the probability of success is. What is Abby's free throw percentage? And I don't know it off the top of my head, but we're going to say she makes it about 85% of the time. So her probability is 0.85. So we can set this up. We're going to look at the probability that x equals 8. That would be the number of successes equals 8. You could just go p of 8, but having that x in there is a little bit more appropriate. Doesn't make much of a difference here, but in statistics it does. And so if you get into the habit, it's a good thing. All right, so she's going to make 8 shots. What's the probability that she makes 8 shots? Wouldn't that be the probability of success, the 0.85 to the 8th power? Because they're independent, so we can just multiply them. 0.85 times 0.85 times 0.85. We get 0.85 to the 8th power. Now, if she makes 8 shots, how many times does she need to miss it for this problem to work? How many times does she have to fail? And that's a weird thought to think of, because you don't think of, well, I have to fail this many times if I want to succeed this many times. But she's shooting 9 baskets, she makes 8 shots, which means she misses it in one of them. And so we have 0.5 one time, and we can multiply those together because they're still independent. So we have 0.85 to the 8th times 0.15 to the 1, the probability of success to the amount of time she makes it, times the probability of failure to the amount of time she misses it. Now this, if we multiplied it together, would give us she makes it 8 times and misses it on the 9th. There's a bunch of ways we could rearrange that. And that would be a combination. 9 choose 8. She has 9 shots. How many ways can we rearrange the 8 successes? And so, at this point, we just need to figure out these numbers, multiply it out. You can plug it into a calculator. 9 choose 8. It's going to be 8. 0.85 to the 8th power is going to be something that I'm not going to do in my head. And 0.15 to the first power is just 0.15. You multiply those, and you get the probability is 0.3679 is the probability that she makes 8 shots. And so the whole hypothesis testing is it would change the question a little bit. It would say, is she doing better than normal? Is this unlikely to happen? In here, we could ask, is she on fire or en fuego, if you will, during this game? And so with the probability of 0.3679 that she'd get 8 shots, yeah, that she's doing better than the statistics, the probability would suggest that she would, because there's a very small probability, or not a very small, a fairly low probability that she would do that just randomly. So it means that she's just nailing it, she's doing better than usual, and it's an awesome game for her. So let's see if we can generalize this a little bit. Let's get the binomial probability formula. So if we have x equals r, some number of successes, out of n trials, because we have n trials, we're successful r times. Let's think back to what we did. We had the probability of success, and then how many times were we successful? So in general, the probability of success is p, and we're successful r times, which means we probably have to fail sometimes. How do we figure out how many times we had to fail? What did we do up here to figure out 1? Subtraction. 9 minus 8. We were successful 8 times out of 9. Subtract, you get 1. So in general, we're going to have q to the n minus r, and then times the combination n choose r. Because we have n, we have to rearrange the r successes. And that's our binomial formula for probability. I know personally, I don't remember the formula quite so well. I remember how it gets put together. We have this many successes, we have this many failures, and we have to do the combination. Now this comes into play with the binomial theorem that we saw in the last slide, because this would be one term of the binomial theorem. We could do, if we look back at this one, we could do 9 choose 0 times 0.85 to the 0, 0.15 to the 9, plus 9 choose 1, 0.85 to the 1, 0.15 to the 9 minus 1, which is 8, 9 choose 7, and we could do each of that, and that would be the term. That would be the probability that she makes 0 shots, plus the probability that she makes 1, plus the probability that she makes 2, plus the probability that she makes 3, all the way up to 9. If we add those together, we get 1, which is awesome, because that would be the probability that she had 9 shots. But each term of the binomial theorem is a piece of the binomial probability. It's fantastic. You should be excited about this because it's awesome. Anyway, let's look at the dice question. Grant's rolling dice. And you're going to try this one. See if you can use the formula and plug in what we know. So Grant is rolling dice. What's the probability that 4 out of 5 rolls will be 6s? Now over here, we had to specify what that probability is. You know what the probability that a roll will be a 6 is. So the P is going to be 1/6. You have 4 and 5. It's the only information you need. See if you can plug it in and come up with a probability. So go ahead, pause this, and come back when you're done. So, did you actually do it? No? Pause it again. All right. So, we want the probability that x equals 4, because we have 4 successes. So it's going to be 5 choose 4, then 1/6 to the 4th. That's our success. And then times 5/6, not 1/5. That's unfortunate. Times 5/6. And then we get an answer 0.003215, which I believe is actually the right answer. My calculator said 5/6. I can't type. It's a bad thing. But this should be the probability. No, I don't have my calculator with me right now to check. So anyway, it should be 0.003215, and that would be the probability of rolling 5 dice and having 4 of them land 6s. Which we'd think that would be a pretty low probability on just one roll of 5 dice, and that makes sense. So how'd you do on that one? Were you able to plug in the numbers better than I can? I hope so. And so, let's move on to the Shelby problem. We're going to do that on the next slide just because there's not much room. So, Shelby is tearing the bottom off a piece of paper. What is the probability that it is perfectly on the line at least 4 out of 5 times? What is different with this question than the other? It's at least. So, we're looking for, it could be perfect 4 times, or it could be perfect 5 times. The nice thing about those two is that they are mutually exclusive, because it will either be right 4 times or right 5 times. It can't be perfect both 4 and 5 times at the same time. That doesn't work. So we'll just find the probability of each of them and then add them together. But before we do that, we do need another piece of information. Let's say she's successful about 90% of the time in tearing. And so you can try this. Set it up. You have to set up 2 of them. Set up the probability that it happens 4 times plus the probability it happens 5 times. And see what you get. Alright, so if there's 2 of them, the nice thing is the 5 times one is way easier. And so your setup should look kind of like this. We have the probability that x is greater than or equal to 4. You could have put x equals 4 or 5 if you really wanted to. We have the 4, 1, 5 choose 4, 0.9 to the 4th times 0.1, then plus the 5, 1, 5 choose 5 times 0.9 to the 5th. 5 choose 5 is just 1, so this is just 0.9 to the 5th, because there's only one way you can rearrange 5 successes out of 5 things. Plug them into your calculator, because you're not going to do these by hand. You get about 0.32805 plus 0.59049. Add them together, and at least 4 out of 5 times, Shelby will be successful. 0.91049. About 91% of the time, Shelby will be able to rip those things perfectly 4 out of 5 times. So, good job, Shelby. Anyway, and you could have found these completely separate and then just added them together afterwards, too. Anyway, one of the problems you actually see how you can do these is on your calculator as well. It's kind of fun. This was 11.6. Again, it's big, weird-looking equations, but there's only one of them, and if you can remember how it gets pieced together, it makes it a lot easier. And there's really only one topic instead of a whole bunch of topics. Anyway, I will see you in class, and enjoy the rest of your day.